Okay, last part, we're going to use technology, even though I'm letting you use technology now. So we're going to be using Desmos. So Desmos is located over here. What we've got is we've got a problem in this case. So we have a table that you can see. It shows the number of years since the shop was opened, and Y is what is known as the profit. So we can see what's happening over the years as we go through to 2017 and how the profit is increasing in some cases and actually decreasing right at the very beginning. So not a whole lot of changes, but you can see what's happening there. So in this case, we can kind of get a good idea of what's happening with the equation. And this actually makes a lot of sense. So I want to make sure that we understand this one. So we want to figure out which is the right or the closest equation that fits the data the best. And I want to show you the problem with technology as we go through. So what I did is I plugged in all of the values there so we can see all of the values there. I'm going to go ahead and change my axes so that we can see it, right? Notice on the x-axis, I still wanted to go between probably, let's say, 1 and 10, or negative 1 and 10, because notice I started mine off at 0 instead of the 2000s. My y-axis, I wanted to go way up. So notice I'm at 72,000 all the way up there. So I want to be able to see the data pretty clearly. So I go 70,000. And I can go all the way up to 110,000. Okay, so we can kind of get an idea. So we can see that this equation here, as we're looking at the different values, we can see what's happening on the screen. So this is a little bit in the way, but we can see that it's a function that's coming down, kind of going up, and then going up as we progress. And notice there's kind of a little bit of a curve. So this is going to curve up and then it's going to kind of curve over. So it's not going to go over the same exact place. Now, how do you graph these things to see what's the best fit? So I know it's got to be a fourth degree function. Now, why do I know that? Because it's coming this way. So it changes directions once, twice, at least 3 times. Okay, so at least 3 times, but it ends up going up again. Notice here that it goes up over on this side as well. But what I think it does, to be honest with you, is I think it goes up, right? Because we started from 0, or this is really my starting point, but we started at this point, we come across over here, and then we come over here and we start heading this way. So I think it's going up in both directions just based on kind of what it's happening. Of course, this doesn't make any sense, time that is negative. So before 2010, before they even opened up the shop, it doesn't. So when we're going through and we're plotting things, we can kind of figure out what's happening with the function. So we've got all these numbers. Now notice if I do an x to the 4th function, it's telling me this is not a very good graph. Now, how do I know that? I look at this r squared, and the higher they can get this number up towards 100%, the better. So I want this number to be pretty high. So notice with this particular equations, I don't have those exact ways of being able to do that. So I might say, okay, I know it's going the same direction, but it looks like it's kind of switching directions a couple of times. I might try to the 6th power and see what happens if I get it up to the 6th power. It's still not making much of a difference with the 6th power or with the 5th power. And you can kind of see that. So this isn't the greatest graph to do. What I would suggest that you do is type in the equations. Notice that we kind of figured out it was a 4th direction, a 4th power equation. So I'm going to plug this one into my Desmos, which is what I did. That's what this equation is here. And if I turn it on, notice we have kind of a good drawing of that particular function that looks like that. Now, notice it kind of misses the point here, so it doesn't kind of curve around and do anything. So this would be probably my best fit function that I can plug in this particular case. But notice that it didn't give me that equation in this case. It kind of skipped over that number and kind of did that. And that's the problem with graphing, is trying to look at data and being able to do that. So I suggest plugging them in, seeing which equation looks the best fit out of the 4 equations that are on here. So in that particular case, I believe it turned out to be D. And then notice this, what's the assumption in 2020? That the revenue continues to follow the polynomial trend, which means it should increase as we go up. Okay, so we can kind of see that. So D, and we can see what's happening with all those different values. I don't know if I necessarily agree that this is the best fit function out of the 4, okay, especially when we're looking at that table there. But that's what they have. So that's what we're going to take a look at. So, okay, let's go to the next one. So let me reset all the activities just in case and move on to the next resource. Okay, average rate of change is a little bit easier. I can figure out the average rate of change when I'm looking at a particular function. So I have all these numbers here, and I have trying to figure it out. In this particular case, what it is it wants to know between 1940 and 2000. So the table shows the minimum wage adjusted to inflate. Okay, for there, we're going to use the graphing tool to plot all those particular points. So what you would want to do is go in and plot those on Desmos and see what's happening. It's not asking you for an equation, but it wants to estimate the average rate of change between 1940 and 1970, but actually we can figure out the exact value. So if we look at it, we're just looking at the slope between those two values. So notice if we have an equation here in Desmos and we're looking at a different equation, I can basically draw a line between these two and try to estimate what that is. So I can see here what the two values are. I can see here, so it's pretty close to 84,000. This one's pretty close to 92,000. So then I would estimate it by saying, okay, that the Y values increase by 8,000 and in the X values increase by 1. So that would mean my rate of change would be around 8,000. That's what we're looking at. Remember, it's Y, the difference in the Y's over the difference in the X's. Okay, so now we kind of go back over here. When we're calculating the actual rate of changes, remember that we just picked the 2 points. So we want the ones between 1940 and 1970. So that would be 9.95 minus 5.7. So we're going to write that out. 9.95 minus 5.17. And we're going to divide it by 1970 minus 1940. Okay, comes out really close to 0.16. So, of course, in that case, it definitely increased, and we think it came out to be 0.16. So notice here, it increased, came out to 0.16. So all we're doing is just calculating a rate of change. So I'm going to give you that equation for the rate of change. That's the only equation I'm going to give you. We've already done stuff like this. Actually, I think we're done with this assignment on this one. Let me just verify that. Yeah. So instead of going over there, I just want to make sure you have the average rate of change equation. So remember, it is y2 minus y1 over x2 minus x1. We've done this one already. So we subtract the y's, make sure that these 2 points coordinate with each other. So the way that I did it was 9.95 minus 5.17 divided by 1970 minus 1940. Okay, so that's what I have on those things. I don't know if my equation's still showing up. Yeah, it does. So we can see that's my equation that we have there. Because we're subtracting the y values divided by subtracting the x values. That's it.